Hey everyone, and welcome back for another deep dive. Today, we're going to be diving deep into an essay by Yorgo Schneepat, and it's all about quantum electrometers. Now I know, quantum anything can sound a little intimidating, but stick with us. It's really fascinating stuff. We're basically talking about devices that can measure electric fields that are so incredibly weak that they can actually detect the charge of a single electron.
Yeah, that's right. It really is a whole new level of precision. And to get there, we have to rely on some pretty wild quantum mechanics.
Okay, so let's back up for a second. I'm going to vaguely remember. Electroscopes. From high school. You know those things with the little gold leaves that would move apart when there was a charge nearby? How did we go from that to these super sensitive quantum gadgets?
Well, you know those early electrometers, like the electroscopes you mentioned, they were pretty limited. I mean, they could tell you if a charge was present, but that was about it. Then came the quantum revolution in the 20th century. And we suddenly had to rethink our whole understanding of electricity.
Right, because quantum mechanics is all about things being quantized, energy, momentum, all that. It's like the universe is playing a game with dice instead of smooth, continuous movements.
Yeah, exactly. And that fundamentally changed how we thought about electric fields. Instead of just these continuous forces, we started to think about them as interactions that involve these tiny packets of energy called photons.
So like light is made of photons. And those are tied into electric fields, too. It's like suddenly realizing there's this whole hidden layer to reality.
Yeah, that's a great way to put it. And in order to really study this hidden layer, we needed new tools. One of the biggest breakthroughs was the development of SQUIDs, superconducting quantum interference devices.
SQUID-DEEDs. Now, that's a name that sounds serious. What makes them so special?
Well, SQUIDers basically super sensitive magnetometers. They can measure magnetic fields with incredible accuracy. And they do this by taking advantage of superconductivity, which is this crazy state of matter where electrical resistance completely vanishes.
Wait, zero resistance. So electricity just flows forever without any loss. That's mind-boggling. But how does measuring magnetic fields help us understand electric fields? I thought those were two separate things.
Well, they are distinct, but they're also deeply interconnected. Whenever you have a changing electric field, it creates a magnetic field and vice versa. It's like two sides of the same coin.
Ah, okay. So by measuring those tiny magnetic field changes, sweeties can indirectly tell us about the electric field. Climate.
Exactly. But here's where the true quantum magic kicks in. Sweeties exploit this concept called quantized magnetic flux. It means that the magnetic field inside a superconductor can only exist in discrete specific values, like steps on a staircase. You can't have a magnetic field that's halfway between two steps.
So it's not a smooth ramp. It's like the magnetic field is forced to snap to these quantized levels. That's wild.
Yeah, and that's what makes squiddies so precise. They can detect even the tiniest jumps in the magnetic field, which corresponds to incredibly subtle changes in the electric field.
So squids were a huge step forward. But I'm guessing they're not the only type of quantum electrometer out there.
You're right. Another fascinating approach uses atom interferometry. It's based on this mind-bending idea that atoms can behave like waves, just like light.
Hold on, atoms acting like waves. I thought they were, solid particles.
That's what classical physics tells us. But the quantum world plays by different rules. In atom interferometry, we literally split a beam of atoms into two, let them travel along different paths, and then recombine them.
Okay, I'm picturing a tiny, tiny version of those double slit experiments they show in physics class, where light creates those interference patterns.
You got it. And the key is that the interference pattern created by these atom waves is super sensitive to any electric fields they encounter along their paths.
So each atom is like a tiny sensor, picking up information about the electric field as it travels. That's insane.
It is pretty amazing. And it lets us measure those electric fields with a level of detail that was unimaginable just a few decades ago.
Right, so we've got SQUIDs using superconductivity and quantized magnetic flux, and we've got atom interferometry exploiting the wave-like nature of atoms. Two completely different approaches, both rooted in quantum weirdness.
That's the beauty of quantum mechanics. It offers this whole new toolkit for understanding and interacting with the world, leading to these incredible technological advances.
And what's even cooler is that all of this complexity is packaged into these devices called quantum electrometers. It's like having a tiny quantum laboratory at your fingertips.
That's a great analogy. But what's really fascinating is what's going on inside these devices.
Okay, I'm ready to peek under the hood. What are the key components of a quantum electrometer?
Let's dive into that after a quick break. We'll explore the inner workings of these technological marvels and how they're shrinking down to the nanoscale.
Sounds great. Stay with us, folks. We'll be right back to continue our deep dive into the world of quantum electrometers. Okay, so before we took a pause, we were about to delve into the nuts and bolts of a quantum electrometer. What's actually going on inside these things?
Well, at the heart of it all is the sensor, which could be a SQI or an atom interferometer, depending on the type of electrometer. This is the component that directly interacts with the electric field we're trying to measure.
Right, those super sensitive quantum detectors we were talking about earlier.
Exactly. But the signals these sensors pick up are incredibly faint, so they need to be amplified. That's where specialized amplifiers come in, boosting the signal without adding too much noise.
I see. So it's like listening to a whisper in a noisy room. You need to amplify the voice without amplifying all the background chatter.
Yeah, that's a good analogy. And once the signal is amplified, we need a way to actually read it. That's where detectors come in, converting the signal into something we can easily interpret, like an electrical or optical signal.
Okay, so we've got the sensor, the amplifier, and the detector. That sounds kind of like a standard setup for any measurement device. What makes a quantum electrometer unique?
You're right, those are fundamental building blocks. But a quantum electrometer also needs a control unit to manage the operation of the sensor and coordinate data acquisition.
So it's like the conductor of an orchestra, making sure everything is working in sync.
Exactly. And depending on the type of sensor, you might also need a cryogenic system to keep things extremely cold. Remember those superconductors and SIGIS? They only work at ultra-low temperatures.
Right. So it's actually a pretty complex system with all these different components working together.
It is quite sophisticated. But what's really remarkable is that researchers are figuring out how to miniaturize these devices. Thanks to advances in nanotechnology.
Wait, miniaturize them? Does that mean we might someday have pocket-sized quantum electrometers?
It's not out of the realm of possibility. We're talking about shrinking down the sensors, the amplifiers, even the cryogenic system.
Wow, that's incredible. So these things that once required bulky lab equipment could someday become as common as smartphones.
That's the exciting potential here. And miniaturization opens up a whole new world of applications.
Okay, let's talk about those applications. What are some of the ways quantum electrometers are being used right now? And what are the possibilities for the future?
Well, with their incredible sensitivity, quantum electrometers have become essential tools in a variety of scientific fields. For example, in quantum computing, they're crucial for characterizing and controlling those delicate quantum bits, or qubits, that are the building blocks of quantum computers.
So they're helping us build the computers of the future.
Exactly. They're also being used in quantum cryptography, where they can detect eavesdropping attempts on secure communication channels.
So they're not only building new technologies, but also making those technologies more secure.
That's right. And then there's nanotechnology and materials science. Quantum electrometers allow us to study materials at the atomic level, understanding their electrical properties in unprecedented detail.
So we're talking about unlocking the secrets of matter itself.
Precisely. And this knowledge can lead to all sorts of innovations, from better batteries to new types of electronics.
It sounds like we're just scratching the surface of what's possible. What other applications are on the horizon?
Well, one area that holds immense promise is medical diagnostics. Imagine being able to detect diseases in their very early stages, even before symptoms appear, by measuring subtle changes in the body's electrical fields.
That would be revolutionary for healthcare.
Absolutely. And in environmental monitoring, quantum electrometers could be used to detect pollutants with incredible sensitivity, helping us protect the planet.
It's amazing to think about the impact these devices could have across so many different fields. But I'm guessing there are also challenges and limitations that need to be overcome.
You're right. As with any cutting-edge technology, there are hurdles to overcome. One of the biggest challenges is scaling up production. While we've made great strides in miniaturizing these devices, mass-producing them while maintaining that high level of precision is tricky.
I see. So it's one thing to build a prototype in the lab, but quite another to manufacture millions of these things. What other challenges are there?
Their extreme sensitivity, while a huge advantage, also makes them vulnerable to noise and interference from the environment. It's like trying to hear a pin drop during a rock concert.
So how do you shield these delicate instruments from all that external noise?
It requires incredibly careful engineering and calibration. Researchers are developing better shielding techniques and noise reduction algorithms to tackle these issues.
It sounds like a constant battle against noise. but one that's worth fighting to unlock the full potential of these devices.
Absolutely. And as this technology continues to evolve, we need to be mindful of the ethical implications.
Ethical implications, what do you mean?
Well, with their ability to detect such minute electrical signals, quantum electrometers could potentially be misused, especially in areas like surveillance and privacy.
That's a good point. The same technology that could be used to develop life-saving medical treatments could also be used for less noble purposes.
Exactly. It's a reminder that with any powerful technology, we need to have open discussions about responsible development and use.
So we've covered the basic building blocks of quantum electrometers, the challenges of miniaturization and noise reduction, and even touched upon some ethical considerations. It's clear that this technology has the potential to be truly transformative.
It really does. And as we wrap up our deep dive, I think it's important to remember that this is a field that's still evolving rapidly. New discoveries and innovations are happening all the time.
That's what makes it so exciting. But before we get too far ahead of ourselves, let's take a closer look at the core quantum principles that make these devices possible.
Great idea. Let's dive into the weird and wonderful world of superposition and entanglement.
Okay, so we've talked about these amazing quantum electrometers, but some of this stuff still sounds like science fiction to me.
Right.
So let's break down these quantum principles that actually make it all work. Let's start with, superposition.
Yeah, superposition. That's the mind-bending concept that a quantum particle can exist in multiple states at the same time.
Right, like Schrödinger's cat being both alive and dead until you open the box.
That's the classic analogy. Although it is a little oversimplified. I mean, the point is this ability to be in multiple states simultaneously. That's a key part of how quantum electrometers work.
Okay, I'm intrigued. How does superposition actually play out in these devices?
Well, think about atom interferometry. We split a beam of atoms, sending them along two different paths. Each path might expose the atoms to a slightly different electric field.
So the atoms are basically experiencing multiple electric field conditions at the same time because they're traveling along both paths.
Precisely. And because they're in this superposition of states, they're interacting with those fields simultaneously. When the two paths are recombined, the resulting interference pattern tells us about those subtle variations in the electric field.
It's like each atom is a tiny scout, gathering information from multiple locations at once.
That's a great way to visualize it. And it's this quantum quirk that allows for such remarkable sensitivity. Classical electrometers just can't compete.
So superposition is one key principle. What's the other one we should wrap our heads around?
Entanglement. This is where things get even weirder.
Entanglement. That's the spooky action at a distance stuff, right? The idea that two particles can be linked even if they're miles apart.
That's the one. And it plays a crucial role in certain types of quantum electrometers, especially those using SWIWIDEs.
Okay, I'm ready to be spooked. How does entanglement help measure electric fields?
Remember how SWIWIDEs rely on those superconducting loops? Well, inside those loops, you have electrons that are entangled. Their fates are intertwined no matter how far apart they are.
So if you poke one of those entangled electrons, the other one reacts instantly, even if they're on opposite sides of the loop.
Exactly. And this interconnectedness makes them incredibly sensitive to any changes in the magnetic field surrounding the loop. And remember, a changing magnetic field is always linked to a changing electric field.
Ah, right. So by monitoring these entangled electrons, we can get incredibly precise information about the electric field, even though we're not measuring it directly. It's like having a pair of tiny spies communicating telepathically.
I love that analogy. It really captures the essence of entanglement. And it's this mind-boggling phenomenon that allows us to make measurements that were once considered impossible.
So to sum it up, we've got superposition, where particles exist in multiple states at once, and entanglement, where particles are linked across space. Two quantum principles that sound like they belong in a science fiction movie, but they're actually the driving force behind these incredible devices.
And it's important to remember that this is just the tip of the iceberg. We're still in the early stages of understanding and harnessing the power of quantum mechanics.
This whole deep dive has been a real eye-opener. We've gone from those basic electroscopes to these quantum electrometers that can detect the faintest whispers of electric fields. It's amazing to see how far we've come.
It really is. And thanks to the work of researchers like Yurgo Schneepat, who wrote the essay we discussed today, our understanding of these phenomena continues to grow.
And who knows what the future holds? Maybe one day we'll all have pocket-sized quantum electrometers letting us explore the world around us in ways we can't even imagine.
I wouldn't bet against it. It's a truly exciting time to be alive and witnessing this quantum revolution unfold.
Well, on that note, I think we've reached the end of our deep dive. Thanks for joining us on this journey into the world of quantum electrometers. And a big thanks to our expert for guiding us through the quantum realm.
My pleasure.
And for our listeners, if you want to delve deeper into this fascinating subject, be sure to check out Jorgo Schneppat's essay. Until next time, keep exploring, keep questioning, and keep that spark of curiosity burning bright.